Okay, hi guys, welcome back. First is the midterm. I guess not everyone care about this because you can choose credit, I guess. Credit, non-credit, general credit. So, well, this is well expected. So, if you're not very happy with the score, that's fine. I mean, you get the credit either way. So first of all is that the you guys did pretty much what I expected. I think I did mention that the median would be around 75, and then yeah, you guys exceed that by 1 point. Okay, thanks for the person that at 76. And then we have the highest is 96, and then 3 of you did very well, above 94. And then the score is well clustered, right? It's here, 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 right? So if it's a letter grade, then it'll be very clear. Okay, of the grade it will be A plus, A minus, and then probably B plus here. Okay, and it's up to you whether you want letter grade or you just want the credit. Okay, and the solution is uploaded to the resource UV Colab, and then also I graded all the exams. You can take a look, and yeah, in general it looks fine. There's nothing, nothing particular I want to talk about. And the final exam will be the same difficulty level, and they will not overlap. Okay, what we have it will not overlap with the content in the midterm. Okay, so the final will be completely, nil, depending. Well, will be based on the content after the midterm. Okay. Any questions regarding the midterm? Okay, and then yeah, if you have questions regarding your score, you can always email me, and then or discuss with me in the office hour. And then one thing is that please don't share the please don't share the solution with other people outside our class, because I need to reuse some of the materials. Okay. Otherwise, if I see some other people are know the solution, so I probably have to increase the difficulty level just to well, if you want the next year students to suffer, okay, you can share with them. Okay, so let's come back to the final chapter in the quantization of light, right? We already covered that to quantize the light, we assume light is trapped inside a pair of mirrors so that we don't have to do integration to infinity. And then the electrical field and magnetic field has the Q and P here. Q and P are supposed later are quantized into position and momentum operators. And then the Hamiltonian, okay, after quantization, the Hamiltonian looks exactly like the harmonic oscillator. And then we did a second quantization, which is also called ladder operator, is to define the annihilation operator. A is called annihilation operator. And then its conjugate transpose is called creation operator. So what the annihilation operator does is that if it acts on n photon state, it will become n minus 1 photon state. So reduce photon number by 1. Creation operator is you act on n state, it gives you n plus 1 photon state. Okay. And then by using the commutation relation between Q and P, you can also get the commutation relationship between annihilation and creation operators. And then you use all this, and then you can calculate the eigenenergy of the nth state is h bar omega n plus 1/2, right? And then n is 0, 1, 2, 3. And 0 means there's no photon, so it's vacuum, okay? And then there's a little bit of energy in the vacuum. And then eventually, okay, how do you get this? How do you get the wave function of all this state? is that you apply the annihilation operator on the vacuum state, and then what that will give you should give you 0, because you cannot have a state lower than the vacuum state. And then this, you plug in the A is defined here, and then P and Q are here, and then you can solve. It's actually a Gaussian function, Gaussian waveform. Okay, so so in this class, well, in the next about 20 minutes, I'll try to kind of wrap up the photon part, okay, and then show you guys, what this can be used for. Okay, so the first thing is that something related to detection, okay, detecting photon, is that if you take a look at this, the Hamiltonian, okay, the Hamiltonian is right, and then the eigenstate, they are right. So then, if you apply this Hamiltonian, okay, plug it into here and then calculate this, what you will see is that the A dagger A, okay, act on state n will give you number n, and then your eigenstate, right? So this is exactly the same as this, okay? So what it tells you is that this operator, okay, you first lower the state by 1 and increase the state by 1. Ultimately, it gives you a number, and this number is a photon number in your system. So this operator here, A dagger A, is called photon number operator, or number operator. Okay, and this is actually very useful, because now imagine if you have a lot of light, okay, coming in and then arrive at your detector, right? And your detector absorbs this photon and create electron, and the electron come out and form current, right? So if you have a perfect detector, then you have one photon creating one electron and no amplification. Then you get your photocurrent I should equal to the number of photons, right? So if now you have a state, okay, you have a state input into your detector, then now classically, what you do is that, okay, you say there's a power level of this light, and then, okay, you have a response of a detector, and you output certain power, or you output certain current. Now, in the quantum picture, what you can do is actually much simpler than that. Okay, you have a quantum state of that, right? And then the current is just the photon number per unit time, right? Per unit time. So that your current now is proportional to your photon number in your state, and then this can equal to, if you are calculating the expected value, then it's expected value of psi, your state, okay, to get the expected value of the photon number, right? And because photon number is the same, because this photon number operator gives you the photon number on nth state, okay? So when you do this integration, it will actually give you the total photon number, okay? And this is how you kind of quantize the detector as well. Okay, not just quantize state, but also the detector. Now the second thing is that in photon, okay, people write people mention like one photon, single photon state, two photon state, vacuum a lot. And then as you can see here, another thing is that because we have this creation and annihilation operator, we know how to add photon into the system and extract photon from the system. The exact waveform of the photon state actually doesn't matter, right? Actually doesn't matter that much, unless you want to directly measure, because if you think about it, what this waveform really means, this waveform means that this value, okay, this value means if you want to measure the electrical field, what is the probability of getting the field with magnitude Q, right? And then in light, usually people don't measure field directly. People measure the power, people measure energy, right? And when you do that, you're actually doing this photon number measurement. You're actually counting all of our detectors, they're actually counting the number of photons. They're not directly measuring the field. So that knowing this waveform actually doesn't do much. Okay, doesn't do much. And then you can actually prove that for most of your the thing you can measure, okay, knowing what the creation and annihilation operator do to your state is enough. Okay, it's good enough for most of the experiment. So then, what people kind of, well, physicists are lazy, right? So what they did is that they don't want to write down psi every time. And then they create a new notation, right? They say the nth photon state, the state that with n photon now can be written as n in a right bracket. Okay, this is just a notation. Okay, this is called Fock state or Dirac notation. Okay, so vacuum would be like this, and this is single photon state, two photon state, and keep going, right? Keep going. And this is just a very common notation, and this state is called Fock state. Now, if we want to completely get rid of the the actual waveform of Q, then one thing we kind of need to know is that we need to know this. We cannot just say this gives us something proportional to this. We need to know the actual coefficient in the front, right? If you apply annihilation operator on nth photon state, and what is and become a n-1 photon state, but there's a coefficient in the front. We need to know that coefficient. And then this coefficient, I showed it in the note, page 20. And the note was actually prepared 3 years ago. And then when I taught this class for the first time, actually I introduced Dirac notation first, and then teach this. Actually, to calculate this in a very efficient way, we actually need Dirac notation. So I'm actually just going to give you guys the answer, and then later, because Dirac notation, we will learn that next week. Okay, so showing you how to calculate this coefficient doesn't make much sense. Okay, so the calculation is kind of the idea is like this. Like the brief idea is like this. Okay. You know this, okay, and then you also know it's complex conjugate. Okay, and then you add them together, and then there's two ways you can calculate it. One is to get One is to, if there's a coefficient in the front, then you know the coefficient square. And then the other way is to flip this using direct notation and get the n out. Okay, so we're not going into the detail here, but then I can write down the answer here. Here is square root of n, okay, square root of n. And then here, okay, is n plus 1. And then you can very easily verify this by seeing, okay, if we're doing on the vacuum state, right, n equals 0, then this act on 0 should be 0, right? And this a act on n, square root of n, right? If n is 0, then it returns to 0. Okay, so you satisfy this one. And then the second thing is you can think of is using this to calculate the photon number operator, right? So now if you have a dagger a act on the n state, okay, the first one acting on it will give you square root of n in the front, a dagger psi n minus 1, right? And then now your creation operator also acts on your state, and that it create a coefficient that is n plus 1, okay, but n is the number of photons in your state, right? So because now the number of photons is n minus 1, so when you plus 1, it becomes n again, right? So n square n, okay. All right, so you can see that it actually agree very well with the vacuum state and also with the photon number operators, right? Okay, now you might ask, okay, this is very good in a way that we can solve the harmonic oscillator, or we can solve the quantization of light using, it's just linear algebra, right? We didn't even solve anything nonlinear, and you don't even need to solve any differential equation, which is great. And you'll see that there are very few cases that you can do this, okay? But then there's actually a deeper meaning here, is how you can kind of understand, well, it's the deeper meaning here is that it provides a mathematical link to between the concept of photon and the actual quantum mechanics. And I'll give an example here to see, what's the application of this. For example, okay, there are some kind of nonlinear optics effect. Nonlinear optics means that the input the output is not linear with the intensity on the output is not linear with the intensity of the input. Okay, so most of the electronics, for example, the transistor, they are nonlinear. Okay, so this process actually can happen in all dielectric material, including your glass, as long as the light is strong enough. For example, if you have a photon 1 and photon 2, okay, they input into your media. And now, okay, and now with some nonlinear interaction, the output become photon 3 and photon 4. Okay, so this photon can have different energy, different momentum, right? Different frequency, so that okay. And so how do you write this down in terms of the creation and annihilation operator? Okay, so the very easy way to do that is that you can say, okay, I write down the interaction, the potential energy of this process, and what this process do is that it annihilate photon 1 and photon 2 and create photon 3 and photon 4, right? So you have to H, and then there's some interaction strength G, and then you say annihilation of photon 1 and photon 2, right? Photon 1 annihilation operator, photon 2 annihilation operator, and then creation operator of photon 4 and photon 3. Okay, so if you apply this to a quantum state, then this term will actually lower, think about it, will lower the photon number in this frequency and that frequency by 1 and increase the photon number from on frequency 3 and 4 by 1. Okay, so it's a way to describe the interaction of light really on a photon basis. Right? It's not like Maxwell equation anymore. You can just write it down as operators. And it turns out that in the fundamental, well, it turns out in the quantum field theory, right, when people talk about the fundamental particles, right, electron, they collide, what will happen? They do exactly the same thing, okay? They actually also create a creation and annihilation operator. And then there, what's interesting is that your wave function there, okay, what is quantized is that your wave function there is no longer, it's not interpreted as the propagative wave, but instead is a field that correspond to the creation and annihilation of a certain particle at a certain position. Okay, and and this is actually kind of a big deal. And then I think it's I think the quantization of light and then all this together won a Nobel Prize somewhere, probably early 2000. But the work was done like in the 1960s. Okay, so let's now talk about the consequence of having this quantization of light. And then the most significant consequence is actually on our understanding of vacuum. Okay, it's actually on our understanding of vacuum, that the vacuum state has energy of half a photon, right? Has energy of half a photon. So this literally means vacuum is not empty. Okay, vacuum is not empty. This is a little bit counterintuitive, but if you think about it, there's nothing weird about it, because you think it's empty, it's just because you can't see it, but then we can't see a lot of things, right? We can't see electron. None of you have seen electron, and then yet you believe it exists because textbook tell you that, right? So you believe in the textbook, and then you believe in electron. The same thing is for the vacuum, right? When people tell vacuum is completely empty, but how do you really know, right? And also, none of us have seen, well, we have seen EM field because light is EM field. But then for the radio frequency field, radio frequency wave, gigahertz wave that we use for our cell phone, right? 4G, 5G, none of us have seen that. Okay, but then you believe it exists because it's working, right? So the critical question here is that, okay, we know that vacuum has non-zero energy. But would that lead to any observable effect on experiment to confirm that exists, right? That's the critical part, right? If we're not able to use radio frequencies for communication, then probably, I guess, half of the population won't believe it exists, right? Although nowadays some of them still don't believe it exists, which is funny. I don't know if you guys know the fact. I think there's a survey done in British a few years ago, and then 33% of the responders think Earth is the center of the universe, and then the sun is orbiting around the Earth. 33%, and yeah, I was just shocked about the the individual freedom level like UK has, right? You can absolutely believe whatever you whatever you want, and then there's no penalty on that. Okay. So for this one, okay, of course, for something that this big, a physicist would obviously want to know if there's some observable effect of the vacuum field. And then the most famous one is the spontaneous emission. Okay, spontaneous emission. So suppose there's the electron in an atom, and then it could be in, well, ground state and excited state, right? To energy level state. And then if it's in the excited state, and suppose it's in vacuum, right? The common understanding is that, well, the original common understanding is that the electron can stay there forever, right? Because it's in vacuum, nothing is interacting with it. But then Albert Einstein was actually the first one to point out that that's not possible, because he did some thermostatistic calculation and showed that there must be a spontaneous emission process exist, otherwise it violates thermal equilibrium. And that's in I think that's in 1916. So it's way before actually quantum mechanics was completed, way before the formulation of a photon. Right, so it kind of shows how, how smart he is, and so how the vacuum fluctuation is connected with the spontaneous emission. One thing you can see is that for the vacuum state, okay, it's actually a Gaussian state, right? So your electrical field is not zero. The electrical field is proportional to Q, and then your probability of your state being at Q is this, right? Amplitude square of this. So what really happened, okay, in vacuum is that there are slight. Probably shouldn't use E1, E2. Okay. There are many of this vacuum fluctuation that has a little bit of electrical field, right? And this electrical field can interact with the electron, right? Electron respond to your electrical field. And then eventually this can cause emission, right? Spontaneous emission from decay from the excited state to the ground state, and then emit a photon. Okay, and people actually have used this theory, okay, to calculate the emission rate, right? For different photon, for different atom, there are different structure and then different energy level, and people actually calculate this and they agree with the theory tremendously well, right? So that's the first proof of actually the vacuum fluctuation does exist, and then it has some effect on our world. And then the second one is the so-called Purcell effect. Okay, Purcell effect. Now, if you guys take a look at the electrical field, or you just take a look at this setup, right? There's a cavity here, and then the ground state, the vacuum in total has an energy of h bar omega divided by 2. It has nothing to do with the size of your cavity. That's a little bit weird, but that's actually true. So what it means is that if you move these two mirrors closer and closer to each other, you're still having the same amount of energy, but then your field is being trapped in a much smaller space, right? So that the energy density of your vacuum will increase. And what that means, if the energy density is increased, then your electrical field and magnetic field will increase, right? So it's the same amount of energy, but then if you trap it in a smaller space, then everything increases, right? So this is something called Purcell effect. Okay, if you put an atom in a pair of mirrors, okay, and then you move the mirror closer and closer to each other, what you will see is that the fluctuation from the vacuum increase, and the atom actually will have faster spontaneous emission rate. Okay, the atom will actually tend to emit faster and faster. And this is actually something has been, I think it's proposed in the 1960s and actually has been observed, many times in many different systems. Okay, and then the third one is something called Casimir force. I don't know if some of you heard of it. Is that when you have two metal plates and then they're very close to each other, then you will actually detect there's a little bit of force in between them. And that force is actually created by this vacuum fluctuation. Okay, and it's kind of very interesting. Okay, now let's talk a little bit of a still unresolved thing of this quantization of light. The idea is that, okay, well, each mode, right, each cavity mode inside the cavity has energy of h bar omega. And then we know that the cavity, okay, actually support just like the string of the violin, right? It supports certain frequency, and then or certain wavelength, and then you know that you only need to satisfy the periodic boundary condition so that the lambda equals to 2L, n lambda equals 2L, n equals to 1, 2, 3, and keep going, right? So it's like when you finish one round trip, reflective finish one round trip, you're returning to yourself. Okay, so in principle, in a pair of cavity, you actually have infinite amount of modes, right? So you have, and each mode have energy h bar omega divided by 2, even its vacuum, right? So it seems that you have infinite amount of energy inside your mirror. Okay, inside a mirror. And then that's a little bit amazing, right? But then, of course, very quickly you can say, okay, but the mirror cannot really be reflective to all the wavelengths, right? The mirror has certain reflectivity rate. For example, the mirror we use is reflective for the visible light, but then it's not for the X-ray, right? X-ray can penetrate it, and then the metal, okay. Metal is pretty good reflector. Metal can reflect X-ray, can also reflect RF. Metal is probably a better one. So you can quickly say, okay, this infinite energy only happens because you assume there's a perfect mirror, but then there's no perfect mirror, so it's fine. But then you can say, okay, but how about this? We push the distance between the mirror to infinity, right? Push it to infinity. And then in between these two mirrors, you still have all these modes, right? You still have all these modes. And then you still have each mode, you still have an energy of h bar omega divided by 2. And if you think about it, when you push it to infinity, what you're doing is that you're actually eliminating the mirrors, because it would take infinite amount of time for the photon actually to hit the mirror and then going backward. Right? So it's almost like if you're pushing the mirror to infinity, it's equivalent to saying that the photon is in free space. Okay, it's traveling, and then it would take billions of years to reach the end of the universe and then being reflected by an imaginary mirror there and coming back. Right? So, and then you'll say, okay, then you can put infinite amount of mirror around our universe, and then there are infinite amount of mode again, and then infinite amount of energy. Right? So So the question really is, okay, you can actually calculate this, is that if you put the actual energy inside the mirror is actually equal to something like this. So lambda L, lambda H is the cutoff wavelength of the reflectivity of your mirror. So it's not perfect mirror. And then L is the distance between the two mirrors. And you can see when L goes to infinity, okay, your vacuum energy goes to infinity. Okay. And so this comes down to a question now, okay, we can't have infinite energy. Well, in theory, well, like our understanding is that we won't have infinite amount of energy. Whether we do have or not is a different question. So what you can do is that, okay, you can actually use the fact that the universe has certain size, right? Universe is not infinite. There's the universe has only been there for about 13 billion years, and then if you think about it, if we all start from a singularity, then the light travels 13 billion years, and that's how large a universe is, okay, on the scale, ignoring all the details of the physics. So then what you can really do is that you can apply that to here, the size of the universe, and then you can get a vacuum energy. Okay, if you put a pair of mirror, okay, at the two end, well, universe doesn't work that way, but then universe, it's more like you imagine it's well, it's not really a content of this class, but we can kind of spend a few minutes on here. So the fact that, you know, the most interesting thing, at least I think, about the universe is that if you look at the star, all the stars are getting away from us, right? That's a Hubble effect. And the only way that can happen is imagine that it's a balloon, right? It's trying to blow up in the two-dimensional balloon, blow up, and then no matter where you are, all the points are getting away from you, right? So it's like an expansion of the total area you have in the balloon. So so that the way that this everything getting away from you can happen in the real world is that we're actually living, well, mathematically, is that everything is on a four-dimensional balloon. Okay, we're on the surface of a four-dimensional sphere, and then that balloon is getting larger and larger, and then because we're only able to observe 3 dimension, not 4 dimension, so we actually can see everything is getting away from us. Okay, and and getting back to here, is that the question that people want to answer, okay, probably will be answered by this or next generation, is that is this vacuum energy the dark energy, right? We know that there's some dark, well, people have, based on observation, people have suggested that there has to be dark energy for the universe to keep growing, keep expanding. And whether this is a dark energy or not, okay, it's actually a very, very interesting question. And there are many different levels of how to answer that question. The first would be, okay, this energy can be created very simply in the lab, right? You put a pair of mirror, then you have vacuum energy here. Okay, so the question here is that does that energy has gravitational effect, right? Because we know that we know that from this very famous Einstein equation, right? E equals mc squared. If you have energy, you have mass, and then if you have mass, you have gravitational effect, right? So if this energy, 0-point energy, doesn't have gravitational effect, then it cannot be the dark matter. It cannot be the dark energy, because the dark energy was suggested to exist because the universe is expanding, right? So, and then also, okay, if this is, then how do you really prove it, right? How do you really prove there is dark energy? And there's a rumor, okay, there's a rumor from from a tutor of a scientist suggesting that one of the, I think it's Italian group, they have some early signals of dark energy, and then they are now double checking their data, and then but then on the other hand, we can't really be overhyped on things like this, because also a few years ago, an Italian group claimed that they saw neutrino having, traveling at a speed faster than light, and that's also a rumor. And then so they double check all their system, and they found that there's actually a latency in the internet that connecting to port, and then that. And then because one of the clock is not really perfectly synchronized with another one, so that they see the speed of light, well, speed of neutrino is faster than speed of light. So when you enter this very, very, cutting edge or state of art fundamental measurement, a lot of things can go wrong. And then so when you see a signal, it doesn't really mean anything. Okay, we see signals every day, but then most of them are just useless. Okay, and hopefully. So the reason that I want to bring this up in an engineering class is that although this is fundamentally a physics question, okay, the mathematics behind this is actually very complicated, but there's a trend nowadays, right? A lot of these fundamental physics problems, questions, very meaningful questions, is actually answered by the joint effort of physicists and engineers. Okay, if you look at the 3 years ago, the detection of gravitational wave, it's actually a very, interesting engineering achievement, right? Building those large laser, 4-kilometer long laser interferometer, and then isolate all the possible vibrations. And then the entire project actually took let me think about it. The seeding idea start from 1970s, and then I think the first time Caltech put some money in it is late 1970s, and then the first signal was detected around 2016. Okay, and then involved thousands of scientists and engineers. And then something like this could also have to use, both the scientists and engineers. And then this can actually happen to you. For example, the black hole detection, black hole image. I don't know if you guys saw the news last year, right? There's people be able to see the black hole image. That there's a glowing ring, okay, and then in the middle there's a dark, and then in that black hole team, again that's a huge team. The one of the critical components, the detector, right, for the signal at the telescope side, was actually fabricated by Bobby Wyckoff's group in UVA, right? So so that you actually, although we're maybe hybrid engineer and scientist, but then you could be part of this something great, and something that can fundamentally change people's understanding of the universe. Okay, so this is all of the photon part. Any questions?